The limits of mathematical explanation. From the enigmatic brain to the ambitious universe and the 11-dimensional quest. The assertion that mathematics, the bedrock of scientific inquiry, might fall short of fully explaining something as intricate as the human brain or even the neural networks of less complex organisms raises a profound and pertinent question. How then can we expect this same tool, however powerful, to unravel the ultimate mysteries of the universe itself? This query strikes at the heart of our epistemological endeavors, forcing us to confront the inherent limitations of our chosen language for understanding reality. While mathematics has undeniably provided the framework for monumental scientific breakthroughs, its capacity to capture the emergent complexities of biological systems serves as a crucial reminder of the potential gulf between fundamental laws and the observable world. This essay will explore this tension, examining the challenges of mathematically describing the brain and the universe, and how the 11-dimensional model, a theoretical construct aiming for a unified description of reality, positions itself within this intricate landscape of explanation. The remarkable success of mathematics in describing the fundamental laws of physics is undeniable. From Newton's elegant equations of motion and gravity to Maxwell's unification of electricity and magnetism and Einstein's revolutionary theories of relativity, mathematics has provided the precise language to articulate the underlying principles governing the cosmos. Quantum mechanics, with its probabilistic wave functions and intricate operators, further solidified the role of mathematics as the essential tool for understanding the behavior of matter and energy at the most fundamental levels. The predictive power of these mathematical frameworks has been staggering, allowing us to not only comprehend the universe's workings but also to manipulate its forces and develop transformative technologies. However, the limitations of mathematics become starkly apparent when we turn our attention to systems characterized by immense complexities, such as biological organisms. The human brain, with its estimated 86 billion neurons, each forming trillions of synaptic connections, represents a level of interconnectedness and dynamic activity that dwarfs even the most sophisticated computational models. The emergent properties of consciousness, thought, emotion and behavior that arise from this intricate network remain stubbornly resistant to complete mathematical description. While neuroscience employs mathematical tools to analyze neural activity, model synaptic plasticity, and simulate brain regions, a comprehensive mathematical theory that explains the subjective experience of consciousness or the full spectrum of human cognition remains a distant aspiration. The challenges in mathematically modeling the brain are multifaceted. Firstly, the brain exhibits emergence, where complex, higher-level functions arise from the interactions of numerous simpler components in ways that are not easily predicted from the properties of those individual components alone. Consciousness, for instance, is not simply the sum of neuronal firings, but a holistic phenomenon that emerges from their orchestrated activity. Secondly, the brain is a highly non-linear system, where small changes at one level can lead to disproportionately large and often unpredictable effects at other levels. This non-linearity makes it exceedingly difficult to capture the brain's dynamic behavior with simple linear equations. Thirdly, feedback loops, both within and between different brain regions, create intricate regulatory mechanisms that are challenging to model mathematically in their entirety. Fourthly, the brain's constant interaction with the environment, shaping and being shaped by sensory input and motor output, adds another layer of complexity that is difficult to isolate and quantify mathematically. Finally, the evolutionary history of the brain, a process of billions of years of adaptation and optimization, has resulted in an architecture that is not necessarily based on clean mathematical design principles, but rather on a complex interplay of genetic constraints and environmental pressures. In contrast, the ambition of a mathematical theory of the universe often focuses on identifying the fundamental laws and entities that underpin all of reality. Theories like general relativity and quantum field theory aim to describe the behavior of elementary particles, fields, and space-time itself, often dealing with more fundamental levels of organization than the emergent complexity of biological systems. The hope is that the universe, at its most basic level, is governed by relatively simple and elegant mathematical structures, even if the emergent phenomena such as galaxies, stars, planets, and ultimately life are incredibly complex. The 11-dimensional model, in this context, is a theoretical attempt to find such a fundamental mathematical structure, a framework that could potentially unify gravity and quantum mechanics by positing a higher dimensional reality from which our four-dimensional space-time and the fundamental forces emerge. However, even in physics and cosmology, the quest for complete mathematical explanations is fraught with challenges. Phenomena such as the precise nature of dark matter and dark energy, the unification of all four fundamental forces, and the singularity at the Big Bang continue to elude a fully comprehensive mathematical description. These mysteries highlight the limitations of our current mathematical tools and theoretical frameworks in capturing the entirety of the universe's complexity. The concept of emergence may provide a crucial link between the fundamental laws described by mathematical models like the 11-dimensional model and the complex behavior of systems like the brain. It suggests that simple rules operating at a fundamental level can give rise to complex and unpredictable phenomena at higher levels of organization. For instance, the intricate patterns of a flock of birds emerge from simple rules governing the movement of individual birds. Similarly, consciousness might emerge from the complex interactions of neurons following relatively simple biophysical laws. While a fundamental theory might describe the underlying rules governing the universe, deriving the specific emergent properties of the brain directly from such a theory remains a monumental challenge, potentially requiring new mathematical tools and conceptual frameworks to bridge the vast gap in scale and complexity. It is also important to recognize that mathematics can provide different levels of explanation. A fundamental theory, such as the 11-dimensional model aspires to be, might aim to explain the underlying rules and structure of the universe at its most basic level. However, different mathematical tools and models are necessary to describe the emergent phenomena that arise from these fundamental laws. Statistical mechanics, for example, uses probabilistic methods to describe the behavior of large ensembles of particles, while computational models and simulations are employed to study complex systems like the brain or climate. A complete mathematical understanding of the universe may therefore involve a hierarchy of models, each operating at different levels of complexity and addressing different aspects of reality. Furthermore, even in highly mathematical fields like physics, intuition, analogy, and experimentation play crucial roles in guiding theory development and interpretation. Mathematics is a powerful tool, but its application to the natural world requires human insight, creativity, and the constant validation of empirical evidence. Our mathematical models must ultimately align with our observations and validation of empirical evidence. The elegance of a mathematical equation, while compelling, must ultimately be grounded in observable reality. Considering the 11-dimensional model, its mathematical sophistication offers a potential framework for a more fundamental understanding of the universe. The hope is that by exploring the intricate geometry and relationships within this higher dimensional space, we can derive the fundamental constants and laws that govern our four-dimensional reality. However, even if the mathematical structure of the 11-dimensional model proves to be internally consistent and elegant, its ultimate validity will depend on its ability to make testable predictions that align with experimental observations. Just as the mathematical framework of general relativity was validated by observations of gravitational lensing and the precession of Mercury's orbit, the 11-dimensional model must eventually connect with the observable universe to move beyond the realm of theoretical speculation. In conclusion, my point about the limitations of mathematics in fully explaining the complexity of the brain is a crucial and humbling reminder of the challenges inherent in our quest to understand the universe. The emergent properties and non-linear dynamics of biological systems like the brain present a formidable challenge for complete mathematical description. While the ambition of a mathematical theory of the universe, such as the 11-dimensional model, rests on the belief that fundamental laws are governed by simpler, more elegant structures, the path from these fundamental laws to the emergent complexity we observe is far from straightforward. Ultimately, our understanding of both the intricate workings of the brain and the grand design of the universe will likely require a multifaceted approach, one that integrates the power of mathematics with the insights of intuition, the guidance of analogy, and the rigorous validation of experimental evidence. The 11-dimensional model, as a mathematical framework striving for a fundamental explanation, represents a valuable avenue in this ongoing quest, but it must ultimately bridge the gap between abstract theory and the tangible reality of the cosmos, acknowledging the profound complexity that arises from even the simplest underlying principles. Thank you for your time. If you like the content we create, please like, subscribe, comment, and share the 11-dimensional model channel with your friends and family.